All right, so let's take a look at the last couple of lessons in Unit 3, Similarity. And these lessons deal with applying what we know about similar triangles to situations so that we can solve problems. All right, in 15.3, Relatively Reasonable, we have two triangles. Triangle ABC is similar to triangle A prime, B prime, C prime. Give reasonable measurements for all three sides of triangle A prime, B prime, C prime. Explain your reasoning. So first of all, we know that they are similar triangles, one, because the problem told us, but also we can see the markings that angles A and A prime are right angles, and then angles B and B prime are congruent. So by angle-angle similarity, we know that those two triangles are congruent. Now, because we know that this is a right triangle, then we also know that we can use Pythagorean theorem, where we have legs squared. That is interesting. Why did it just disappear? I do not know. All right, let's try that again. Actually, I'm going to do it over here because I think it might be partly because I'm trying to write on a picture, and sometimes that doesn't work very well. So leg squared plus leg squared equals hypotenuse squared. All right, so we have 6 squared plus 8 squared. So we have 36 plus 64, which is 100, which is the same thing as 10 squared. So this side has to be 10. Okay, we know what that is. But the problem says give reasonable measurements for all three sides of triangle A prime, B prime, C prime. Well, if you remember what we talked about before with the Pythagorean triple, we have 3, 4, 5 is a Pythagorean triple, where 3 is a leg, 4 is a leg, and 5 is a hypotenuse. And so any multiple of that is going to be a right triangle. And so 6, 8, 10 is a multiple of that, because if you take 3, 4, 5 and multiply them all by 2, you get 6, 8, 10. So we know that a 3, 4, 5 would be a similar triangle. So you could also look at it as, okay, well, if I divide 6 by 2, I get 3. So my scale factor, yeah, it's because I'm trying to write on that picture. Let's see, maybe I can write just above it, maybe, I don't know. Our scale factor is 1/2. So half of 6 is 3, half of 8 is 4, and half of 10 is 5. So that would be a reasonable measurement for those three sides because it's the same scale factor for all three sides. But again, you can also remember the Pythagorean triple in this particular problem. Okay, let's take a look at the next part of the lesson, 16.2, bank shot. You need to make a bank shot. Sketch the path of the cue ball so it will bounce off the bottom side and knock the solid orange 5 ball into the upper right corner pocket. Well, what are they talking about? This is where we need to go to our website. And I'm going to do a little split screen here so we can see both sides. And so here, and you have this applet if you want to play around with it. But we have here an applet where we can move things around. So we've got this white ball here, right? And we are trying to sketch the path of the cue ball where A is, so that it will, well, this isn't really a ball, but this is where the cue ball is going to bounce off the side of the pool table. And then we want it to hit that orange 5 ball, which is where point B is, so that it will go into the pocket, right? And so we can trace different segments and the angles, right? So we can slide this around and see, okay, well, what's going to work? What do we think is going to work? So think about this. We're talking about similar triangles here, right? So we know that where the pockets are on the bottom, the left pocket and the right pocket, those are right angles there. And so we need to think about what kind of angles do we want here where the cue ball is going to hit the side of the pool table. And so you can play around with that and kind of guess what you think is going to happen. We can also take a look at more controls. And there we can say, okay, well, if we think this is the path right here, This is the path. That's what's going to make the ball go in. Well, we can take a look at the actual segment and, oh, it's not going to hit that orange 5 ball directly on. So it might not actually go in the pocket because it's not hitting it at the right angle. So what do we need to do? If I slide this way, notice that now it's above, right? So I need to get it just right. And what do you see would probably be true, or would have to be true about those two angles where point C is in order for the path of the cue ball to hit that orange 5 ball? Okay, so look at those two triangles. So the measures of the triangles, and actually it might be better to take a screenshot because then we can just write right on that picture. So if we look at these angles, we know that these two are congruent, right? And so then these two must be congruent because these were right angles right here, right? And so how do we find the measure of that angle? All right, so we would take 180 minus 90, which is 90. So then 90 minus 35.54. That's what we need to do to find that other angle, okay? So let's come back over to our notes. And so we've got these two triangles. They look like that. And this is point A, this is point C, and this is point B. Those are right angles, okay? So we know that this angle right here is 35.54, and this one is 35, and it should be 0.54. It's pretty close, 35.53. So calculate the exact point on the bottom, which is what we did, and then precisely draw the path of the ball. All right, so then we know that this measure has to be 90 minus 35.54, which is going to be, let's see, 54.46 degrees. That would be the angle up there at B and at A as well. Okay, so using this slider can kind of help you to see, okay, where's the path of the ball actually going to go? Because when you take away the actual path, it looks like the path of the ball is going to hit that orange 5 ball every time, but that's not the actual path of the ball. You need to have congruent angles there to be able to make sure that you hit that ball dead on. And that actually is what pool players do. They don't break out a protractor and measure the angles, but they've gotten so good that they can figure out those angles. That's really what they're doing. They might not do it mathematically, but they're figuring out those angles to know where that ball is going to go. Same thing is true in like mini golf. It's all about the angles of where the ball is going to hit the side of the wall to be able to bounce off and go in the right direction. And that's kind of what this Are You Ready for More is talking about. So if you want to take a look at that and try to figure out a path of the ball so that it would go in the hole after just one stroke, go for it. All right, let's take a look at the last part of this. So we're going to go here to indirect measurement. Now here is where we can use similarity to indirectly measure various objects. All right, so I want to go back to my calculator. Okay, so you can actually use mirrors to figure out the height of a tall object. So if you place a mirror, say this is you place a mirror on the ground, and then you find the spot to stand where if you're looking into the mirror, you can see the top of the object that you are looking at. So in this case, it's a building. Okay, so once you find that spot on the ground where you are looking in the mirror and you can see the top of that object, you now have similar triangles because you know that both you and the object form a right angle, Okay, so you can't be leaning over, but you're forming a right angle with the ground. Okay, and then the angle that you are looking into the mirror is the same as the angle of the top of the building to the mirror. All right, so we've got congruent angles here, so we have angle-angle similarity there. So what we can do is if we want to know this height, right, and we know our own height, okay, we can figure out what the height is of this object, okay? So we can take our own height up to eye level, because remember, we're not looking from the top of our head, but we're looking from eye level, and we can divide that by our distance from the mirror, because both of those things are measurable. We can have somebody measure us up to our eye, and then we can measure our distance from the mirror. Then we can also measure the distance the building is from the mirror, or the object. Actually, we don't need that anymore. The distance the object is from the mirror. And that will give us the height of the object. So all of these measurements we can actually measure except for the height of the object. So we could measure all of those highlighted measurements and then solve using algebra to find the height of the object. All right, so let's just suppose that our eye level is at 5.5 feet. We'll make it easy, 5.5 feet. And let's say that we are standing 7 feet from the mirror and that the building, we'll say is 100 feet from the mirror, okay? So we can say our own height up to eye level was 5.5. Our distance from the mirror was 7. The height of the object, which we don't know, over the distance the object is from the mirror. And now we have a simple algebra problem to solve. So we're going to multiply both sides by 100. Okay. And then we're going to bring in our calculator. Okay. And so we're going to do 100 times 5.5. And then we are going to divide, actually, 100 times 5.5, and I'll hit enter there. Then I'm going to take that answer and divide by 7. And so the height of that object is approximately 78.57 feet. So just over 78.5 feet. Which would be really hard to try to take a tape measure and measure. Okay, so this is where we can indirectly measure the height of a tall object that we wouldn't really be able to physically measure.